In the last section, we saw how procurement triggers the flow of materials through a supply chain. Ideally, materials move smoothly and continuously, controlled by the methods we described in section 8. But in reality, there are always delays when materials stop moving. Whenever materials wait in the supply chain, they form stocks. All organizations hold stocks of some kind, whether it is a shop that stocks goods for customers to look at, a chef with stocks of ingredients in the pantry, a market research company with stocks of information in a database, or a bank with stocks of cash held in reserve. An inventory is a list of things held in stock, but there is some confusion and people often use it to mean the actual stock. Every organization holds stocks, even those offering intangible services, but manufacturers hold particularly large amounts. Organizations do not want to eliminate stocks, but they want to control them properly, and they do this by efficient stock control. This function is known by several names, particularly inventory control or inventory management. We describe material requirements planning and just-in-time as dependent demand systems for controlling materials. These automatically define ordering policies and set stock levels. The alternative approach assumes independent demand, where the total demand for an item is made up of loads of separate demands that are not related to each other. With independent demand systems, there is no obvious ordering policy, and managers have to decide when to place orders and how much to order. This is a part of their work in designing short-term schedules. A number of standard models can help with these ordering decisions, generally by finding the best balance between various costs. In particular, they look for answers to three basic questions. What items should we stock? No item, however cheap, should be stocked unless the benefits outweigh the costs. So organizations should never add unnecessary new items to stock, and they should make regular searches to remove obsolete or dead items. When should we place an order? This depends on the inventory control system used, type of demand, high or low, steady or erratic, value of the item, lead time between placing an order and receiving the stock, supply reliability, and a number of other factors. How much should be ordered? Large infrequent orders give high average stock levels, but low cost for transport and administering orders. Small frequent orders give low average stocks, but high cost for transport and administering orders. The first of these questions is a matter of good housekeeping, simply avoiding stock that is not needed. The rest of this section looks for answers to the other two questions. Stock as a buffer. As so many people consider stocks to be a waste of resources, we should ask why organizations still hold them. The answer is that they provide an essential buffer between supply and demand. Both the supply of materials and demand can be variable and uncertain, and stocks give a cushion between them. Imagine the food delivered to a supermarket. This comes in large quantities, perhaps a truckload a day, but it is sold in much smaller quantities to individual customers throughout the day. There is clearly a mismatch between supply and demand, and stocks are needed to give a cushion between them. Stocks held on the shelves and in storerooms allow the supermarket to continue working efficiently, even when delivery vehicles are delayed or there is unexpectedly high demand from customers. We can be a bit more specific and list the following reasons for holding stocks. To act as a buffer between different parts of the supply chain. To allow for demands that are larger than expected or at unexpected times. To allow for deliveries that are delayed or too small. To take advantage of price discounts and large orders. To allow the purchase of items when the price is low and expected to rise. To allow the purchase of items that are going out of production or are difficult to find. To allow for seasonal operations. To make full loads and reduce transport costs, and to provide cover for emergencies. Let's now see the types of stock. Just about everything is held as stock somewhere, whether it is raw materials in a factory, finished goods in a shop, or tins of baked beans in your pantry. We can classify these stocks as raw materials, the materials, parts, and components that have been delivered to an organization but are not yet being used. Work in progress, materials that have started but not yet finished their journey through the organization's operations. And finished goods, goods that have finished the process and are waiting to be shipped out to customers. Nationally, there are roughly equal amounts of raw materials, work in progress, and finished goods stored. But this is a fairly arbitrary classification, as one company's finished goods are another company's raw materials. Some organizations, notably retailers and wholesalers, have stocks of finished goods only, while others, like manufacturers, have all three types in different proportions. Some items do not fall easily into these categories, so we can define two other types: spare parts for machinery, equipment, and so on, and consumables such as oil, fuel, paper, and so on. The usual approach with independent demand has managers analyzing the inventory system and looking for ordering policies that minimize the total cost. A rule of thumb says that the total cost of holding stock is around 25% of its value a year. You might think that minimizing this cost is the same as minimizing the stock, but this is not necessarily true. If a shop holds no stock at all, it certainly has no inventory costs, but it also has no sales and effectively incurs another cost of losing customers. Then a reasonable option is to balance the cost of holding stock and making sales with the cost of having no stock and losing sales. Before going into more details, we should look at the different costs of stock. They are usually divided into four types. Unit cost, the price of an item charged by the supplier, or the cost to the organization of acquiring 1 unit of the item. It may be fairly easy to find this by looking at quotations or recent invoices from suppliers, but it is more difficult when several suppliers offer slightly different products or offer different purchase conditions. If a company makes the item itself, it may be difficult to get a reliable production cost or set a transfer price. Reorder cost, the cost of placing a repeat order for an item. This might include allowances for preparing an order, correspondence, delivery, insurance, receiving, unloading, checking, testing, use of equipment, and follow-up. Sometimes a range of other costs can be included, such as quality control, sorting, repackaging, movement of received goods, and so on. In practice, the best estimate for a reorder cost often comes from dividing the total annual cost of the purchasing department by the number of orders it sends out. Holding costs, the cost of holding 1 unit of an item in stock for a unit period of time. The obvious cost is startup money, which is either borrowed, in which case there are interest payments, or it is cash that could be put to other uses, in which case there are opportunity costs. Other holding costs are for storage space, risks, and services. These costs vary widely. Shortage cost occurs when an item is needed but it cannot be supplied from stock. In the simplest case, a retailer loses direct profit from a sale, but the effects of shortages are usually much wider and include lost goodwill, loss of reputation, and loss of potential future sales. Shortages of raw materials for production can cause disruption, rescheduling of production, retiming of maintenance periods, and laying off employees. Shortage costs might also include payments for positive action to remedy the shortage, such as expediting orders, sending out emergency orders, paying for special deliveries, and so on. It can be difficult to get reliable figures for any inventory costs, but shortage costs cause particular problems. These can include so many intangible factors that it is difficult to agree a reasonable value. Most organizations take the view that shortages are expensive, so it is generally better to avoid them. In other words, they are willing to pay the relatively lower cost of carrying stock to avoid the relatively higher cost of shortages. Unfortunately, this defensive approach tends to increase the amount of stock, particularly when there is uncertainty. Now let's explore an example. Jane is a purchasing clerk at ABC Company. She earns around $16,000 per year, with other employment costs of $3,000, and has a budget of $6,200 for telephone, stationery, and postage. In a typical month, Jane places 100 orders. When goods arrive, there is an inspection that costs about $15 per order. The cost of borrowing money is 9%, the obsolescence rate is 5%, and insurance and taxes average 4%. What are the reorder and holding costs? The total number of orders a year is 1,200. The reorder cost includes all costs that occur for an order, and they are salary $13.33 per order, employment costs $250 per order, expenses $5.17 per order, and inspection, which is $15 per order. Adding all those costs together gives the reorder cost of $36 per order. Holding costs include all costs that occur for holding costs, and they total of 18% of stock value a year. Changing value over time. At first sight, the value of something held in stock seems to remain constant over time. You paid $40 for a component, so this is its value. But it is easy to see that the value really changes. If you have a stock of newspapers, they have no value when the next edition arrives. Food gets out of date, and conversely, a tank of oil might rise in price, and inflation might increase the cost of materials. A particular problem here is obsolescence, which refers to stock that has been kept in storage so long that it has little or no value. You can imagine this with spare parts for equipment that has been replaced, or food that is past its sell-by date. There is a general trend for products to have shorter life cycles and a corresponding increase in the risks of obsolescence. Managers clearly want to avoid obsolescence, and the way to do this is not to keep materials for long periods, but to keep them moving as fast as possible. The rate of movement is usually measured in terms of turnover, where the stock turnover is the annual amount spent on stock divided by the average value of stock held. For example, if a company spends $1,200 a year on stock and the average value held is $20,000, its stock turnover is 6. This means that an average item is replaced 6 times a year, and each unit stays on the shelf for 1/6 of a year or 2 months. If the value of an item changes over time, this raises questions about the value of stock held. A company must know this, as stock forms part of the assets that are recorded in its accounts. Is the stock worth the amount you actually paid for it, the amount you would have to pay to replace it, the amount you can sell it for, or some other value? In practice, there are several accounting conventions, with the most common based on the amount actually paid. Variations on this are actual cost, when it is possible to identify each unit remaining in stock and the amount paid for it. This works with small number of expensive items, such as cars and antiques, but most stocks have larger numbers of identical units. First in, first out assumes that stock is sold in the order it was bought, so the remaining stock consists of the most recent purchases. Last in, first out assumes that the latest stock is used first, so the remainder is valued at earlier acquisition cost. Replacement cost. This is the full cost of replacing units at the current price. And average cost. This finds the average cost over some period. The economic order quantity is the optimal size for an order in a simple inventory system. This analysis for this was done early in the last century, and it remains the best way of controlling many stocks with independent demand. It is flexible and easy to use and gives good guidelines for a wide range of circumstances. Imagine a single item that is held in stock to meet a constant demand of D per unit time. Assume that we know the unit cost U, reorder cost R, and holding cost H, but the shortage cost is so high that no shortages are allowed and all demands must be met. The item is bought in batches from a supplier who delivers after a constant lead time. We want to calculate the best order quantity Q. There is no point in carrying spare stock, so we time orders to arrive just as existing stocks runs out. Then we get a series of stock cycles where the stock level follows the sawtooth pattern shown in this figure. At some point an order of size Q arrives. This is used at a constant rate D until no stocks is left. We can find the total cost in each period of time by adding the four components of cost: unit, reorder, holding, and shortage. No shortages are allowed, so we can ignore this component. The number of units bought each period is D, so multiplying this by U gives the unit cost component UD. The average stock level is Q divided by 2, so multiplying this by H gives the holding cost component, HQ divided by 2. The average number of orders in each period is D divided by Q, and multiplying this by R gives the reorder cost component, RD divided by Q. Adding these cost components together gives the cost per period, which is unit cost component plus a reorder cost component plus holding cost component. The unit cost component does not vary with the order size, but if you plot the other two components separately against Q, we get the results shown in this figure. Here you can see that the reorder cost component falls as the order size increases, confirming that larger orders give fewer orders and lower reorder cost components. The holding cost component rises linearly with order size, confirming that larger orders give higher stock levels and higher holding cost components. Large infrequent orders give high holding cost component and low reorder cost component. Small frequent orders give low holding cost and high reorder cost component. Adding the two cost components gives a total cost curve that is an asymmetric U-shape with a distinct minimum. This minimum variable cost identifies the optimal order size. The minimum cost occurs when the holding cost component equals the reorder cost component, or RD divided by Q equals HQ divided by 2. We can use this last observation to calculate the economic order quantity, as rearranging the equation gives this result. EOQ is square root 2 multiplied by R by D divided by H, where D is the demand per unit time, R is reorder cost, and H is holding cost per unit of time. Now let's continue with one example. Jane buys stationery for ABC Company. The demand for printed forms is constant at 20 boxes a month. Each box of forms costs $50. The cost of processing an order and arranging delivery is $60, and the holding cost is $18 per box per year. What is EOQ, total cost per year, and the length of the stock cycle? Listing these values we know in consistent units, we find D 240 units a year. U is $50 a box, R is $60 per order, and H is $18 per box per year. Substituting these values into the economic order quantity formula gives 40 units, so Jane should always order 40 boxes at a time. Then the cost is the unit cost component plus reorder cost component plus holding cost component, which gives us $12,720 a year. Jane buys 40 boxes at a time, so the average stock level is 40 divided by 2, which is 20 boxes. Buying 40 boxes at a time and using 20 boxes a month means that the stock cycle is 2 months long, meaning that Jane places an order every 2 months. In general, the length of the stock cycle is T, which is Q divided by D. In this case, is 1/6 years or 2 months. When an organization buys materials, there is a lead time between placing the order and having the materials arrive in stock. This is the time taken to prepare an order, send it to the supplier, allow the supplier to make or assemble the materials, and prepare them for shipment. Ship the goods back to the customer, allow the customer to receive and check the materials, and put them into stock. Depending on the circumstances, this lead time can vary between a few minutes and months or even years. Suppose the lead time L is constant. To make sure that the delivery arrives just as stocks is running out, we have to place an order a time L earlier. The easiest way of finding this point is to monitor the amount of stock remaining and place an order when there is just enough to last the lead time. With constant demand D, this means that we place an order when the stock level falls to LD, and this point is called the reorder level or ROL. The reorder level is the lead time multiplied by demand. In practice, inventory control systems keep a continuous record of the stock on hand, updating this with every transaction and sending a message when it is time to place an order. Ordinarily, this message is sent to a purchasing department. With e-procurement, the message is sent directly to the supplier. Now let's explore one example. Demand for an item is constant at 20 units a week. The reorder cost is $125 per order and holding cost is $2 per unit per week. If suppliers guarantee within 2 weeks, lead time within 2 weeks, what is the best ordering policy for the item? So let's find the variables. D is 20 units a week, R $125 per order, H is $2 per unit per week, and L, the lead time, is 2 weeks. Substituting this gives the economic order quantity of 50 units. Reorder level is LD, which is in this case 40 units. So the best policy is to place an order for 50 units whenever stock falls to 40 units. This calculation for the reorder level works well provided the lead time is shorter than the stock cycle. In the last work example, the lead time was 2 weeks and the stock cycle was 50 divided by 20, 2.5 weeks. But suppose the lead time is raised to 3 weeks and the reorder level becomes 60 units. The problem is that the stock level never actually rises to 60 units, but varies between 0 and 50. To get around this, we have to recognize that the calculated reorder level refers to both stock on hand and stock on order. So when it is time to place an order, the stock on hand must equal the calculated reorder level minus any outstanding stock on order. In the example, the order quantity is 50 units, so lead time of 3 weeks would have one order of 50 units outstanding when it is time to place another order. Our reorder level is lead time demand multiplied by demand minus stock on order, which is 10 units. An order of 50 units should be placed whenever actual stock falls to 10 units. Because the lead time is longer than the stock cycle, there will be always at least one order outstanding. A common problem is that the economic order quantity is an awkward size. For instance, it might suggest that a garden center order 88.3 wheelbarrows. The center could round this to 88 barrows, but might prefer to order 90 or even 100. So does this rounding have much effect on overall costs? In practice, the total cost curve is always shallow around the economic order quantity, which means that costs rise slowly. If we order between 64% and 156% of the economic order quantity, the variable cost will still be within 10% of the minimum. If we order between 54% and 186% of the economic order quantity, the variable cost will be within 20% of the minimum. This is one reason why the EOQ analysis is so widely used. Although the calculation is based on a series of assumptions and approximations, cost rises slowly around the EOQ, and it is a good guideline in many different circumstances. Logistics and supply chain managers are often under pressure to become more flexible, and one way of doing this is to have small, frequent deliveries. But to reduce the size of the economic order quantity, they have to lower the reorder costs. The economic order quantity is proportional to the square root of the reorder cost, so to halve the EOQ, managers would have to reduce the reorder cost to a quarter. This could be unrealistic. Some managers might simply choose to work with orders that are smaller than the EOQ and accept the costs are only a bit higher than optimal. If they actually set about reducing the reorder cost, a practical way is to combine orders for different materials. Combining orders, for example, 4 orders to a single wholesaler might effectively reduce the reorder cost by a quarter and half order size. This works when transport and other fixed costs from most of the reorder cost. But it is less effective when administration costs are dominant. It also reinforces the move towards using fewer suppliers. Now let's explore one example. ABC Company notices that demand for one of its products is constant at 500 units a month. Unit cost is $100 and shortage costs are known to be very high. The purchasing department sends out an average of 3,000 orders a year, and their total operating costs are $180,000. Any stocks have financing charges of 13%, warehouse charges of 8%, and other overheads of 9% a year. The lead time is constant of 1 week. What is the best ordering policy for the product? Second, what is the reorder level? Third, what is the reorder level if the lead time increases to 3 weeks? What range of order size keeps variable cost within 10% of optimal? And what is the variable cost if orders are placed for 200 units at a time? Now let's find the values. D is 6,000 units a year. Unit cost is 100 per unit. R is the annual cost of purchasing department divided by the number of orders a year, which is $60 per order. H is $30 per unit per year. And L, the lead time, is 1 week. So now we find the best ordering policy by substituting this value into the equations. The EOQ is 154.9 units. Cycle length, which is Q divided by D, is 1.3 weeks. Variable cost a year are $4,647 a year. And the total cost, which are UD plus variable costs, is $604,647 a year. What is the reorder level? The lead time is less than the stock cycle, so the reorder level is L multiplied by D, which is 115.4 units. The optimal policy is to order 154.9 units whenever stock falls to 115.4 units. If the lead time increases to 3 weeks, there will be 2 orders outstanding when it is time to place an order. Then reorder level is LD minus stock on order, which gives 36.4 units. Next, to keep variable cost within 10% of optimal, the quantity ordered can vary between 64% and 156% of the economic order quantity. So this is 0.64 multiplied by 154.9 units to 1.56 multiplied by 154.9 units, or 99.1 units to 241.6 units. And lastly, if orders are placed for 200 units, then the variable cost a year could be $4,800 a year. The economic order quantity has been around for a long time, and it is still the basis of most inventory systems for independent demand. Among its advantages are that it is easy to understand and use, gives good guidelines for order size, finds other values such as cost and cycle lengths, is easy to implement and automate, encourages stability, and it is easy to extend, allowing for different circumstances. On the other hand, there are a number of weaknesses, as it takes a simplified view of inventory systems, assumes demand is known and constant, assumes all costs are known and fixed, assumes a constant lead time and no uncertainty in supplies, gives awkward order sizes, assumes each item is independent of others, and does not encourage improvement in the way that just-in-time does. We can overcome some of these problems by developing more complicated models, and in the next lectures we'll take one step in this direction. The economic order quantity model assumes that demand is constant and known exactly. In practice, it can vary widely and unpredictably. When the variation is small, the EOQ model still gives useful results, but as the variation increases, its results get worse. You can see why this happens from the reorder level. An order is placed when stock falls to the reorder level, which is calculated as the average lead time demand. But when the actual demand in the lead time is above average, stock will run out before the next delivery arrives. By definition, demand is above average half the time, so this means that there are shortages in half the stock cycles. Conversely, demand is below average half the time, so there will be unused stock at the end of the other half of stock cycles. The shortages gives most concern, as few managers would be pleased by a system that only met the demands of half their customers. A way around this is to hold extra stocks above the expected needs to add a margin of safety. Then organizations increase their holding cost by a small amount to avoid the higher shortage cost. These safety stocks are used when the normal working stock runs out. They have no effect on the reorder quantity, which is still defined by the EOQ, but do affect the time when an order is placed, as shown in this figure. In particular, the reorder level is raised by the amount of the safety stock to give. Reorder level is LD plus the safety stock. Higher safety stock give a greater cushion against unexpectedly high demand and reduce shortages. But they also increase holding costs, so managers have to balance the cost of holding safety stock with the cost of shortages. Unfortunately, shortage costs are so difficult to find that they are usually little more than guesses. An alternative approach relies on manager judgment to set a service level, which measures the likelihood that a demand can be met from stock. An organization typically gives a service level of 95%, which means that it meets 95% of orders from stock and accepts that 5% of orders cannot be met. The service level needs a positive decision by managers based on their experience, objectives, competition, and knowledge of customer expectations. There are really several ways of defining service level, but we will take it as the probability of not running out of stock within a stock cycle. This is the cycle service level. Now suppose that demand for an item is normally distributed with a mean of D per unit time and standard deviation of sigma. When the lead time is constant at L, the lead time demand is normally distributed with mean of LD, variance of sigma powered by 2, L, and standard deviation of sigma squared root L. The size of the safety stock depends on the service level that manager set, as shown in this figure. To be specific, when lead time demand is normally distributed, the safety stock is Z multiplied by sigma square root L, where Z is the number of standard deviations away from the mean. Then we can use any statistical package of tables to find the probability of running out of stock with any specific safety stock. To give some examples, if Z is 1, this gives a stock out in 15.9% of stock cycles. If Z is 2, gives stock outs in 2.3% of stock cycles, and so on. When demand varies widely, the standard deviation of lead time demand is high, and very high safety stocks are needed to give a service level anywhere close to 100%. Managers usually choose service levels that reflect the importance of each item, so very important items might have levels around 99%, while less important ones are 95% or even lower. Now let's explore an example. ABC Company runs a retail shop to sell a range of kitchen cabinets. The demand for cabinets is normally distributed with a mean of 200 units a week and a standard deviation of 40 units. The reorder cost including delivery is $200, holding cost is $6 per unit per year, and lead time is fixed at 3 weeks. Describe an ordering policy that gives the shop 95% cycle service level. What is the cost of holding the safety stock in this case, and how much does the cost rise if the service level is set at 97%? Let's now calculate the values. The demand is 10,400 units a year. Sigma, 40 units, R, $200 per order, H, $6 per unit per year, and the lead time is 3 weeks. Substituting these values gives the EOQ 833 and reorder level 600 plus the safety stock. For a 95% service level, Z is 1.64 standard deviations from the mean, and we take this from the standard tables. Then the safety stock is 114. So the best policy is to order 833 units whenever stock falls to 600 plus 114, or 740 units. On average, orders will arrive when there is 140 units minus the safety stock minus left. The cost of holding the safety stock is $684 per year. So for a 97% service level, Z is 1.88 and the safety stock will be 130 units. So in this case, the holding cost of the safety stock would be $780 a year. The EOQ analysis defines a fixed quantity that is always ordered when stock falls to a certain level. A heating plant, for example, may order 25,000 liters of oil whenever the amount in the tank falls to 2,500 liters. These systems need continuous monitoring of stocks to notice when they fall to the reorder levels, so they are best suited to low irregular demand for relatively expensive items. An alternative periodic review system orders varying amounts at regular intervals. For instance, at the end of each day, a shop might order replacement for everything that was sold during the day. The operating cost of this system is generally lower and it is better suited to high regular demand of low-value items. When the demand is constant, these two systems are the same, but differences appear when demand varies. We can show this by extending the last analysis and looking at a periodic review system where demand is normally distributed. Then we are looking to answers for two questions. Firstly, how long should the interval between orders be? This can be any convenient time, and organizations typically place orders at the end of every week or every morning or at the end of a month. If there is no obvious cycle, they might aim for a certain number of orders a year or some average order size. One approach is to calculate an economic order quantity and then find the period that gives orders of about this size. The decision is largely a matter for management judgment. Secondly, what is the target stock level? The system works by looking at the stock on hand when an order is due and ordering an amount that brings this up to a target stock level. So order quantity is target stock level minus stock on hand. At the end of a month, a company might have 10 units remaining of an item with a target stock level of 40, so it orders 30 more units. We can calculate the target stock level by extending our previous analysis. Suppose the lead time is constant at L. When an order is placed, the stock on hand plus the order must last until the next order arrives. When placing an order at point A, for example, managers have to make sure that there is enough stock to last until the next order arrives at point B, which is the order period T plus the lead time. Now assume that the demand in each period is normally distributed with a mean D and variance sigma, and that both the order period and the lead time are fixed at T and L respectively. Then, using the same arguments as before, for the demand over T plus L periods has mean D multiplied by T plus L. The variance is sigma powered by 2 multiplied by T plus L, and the standard deviation is sigma square root T plus L. Then we can define a safety stock as the Z multiplied by sigma square root T plus L, with target stock level calculated using this formula. Now let's see an example to see how this works. Demand for an item has a mean of 200 units a week and standard deviation of 40 units. Stock is checked every 4 weeks and lead time is constant at 2 weeks. Describe a policy that will give a 95% service level. If the holding cost is $20 per unit per week, what is the cost of the safety stock? And what is the effect of a 98% service level? Now let's make the calculations. D is $200 units, sigma 40 units, H $20 per unit per week, T is 4 weeks, order period, lead time 2 weeks, and T plus L is 6 weeks. For a 95% service level, Z is 1.64, which we can find from a standard tables. Then the safety stock is 161 and the target stock level is 1361. When it is time to place an order, the policy is to find the stock on hand and place an order with the size for 1361 minus stock on hand. For example, if there are 200 units in stock, we place an order for 1161 units. The safety stock is not normally used, so the cost of holding it is $3,220 a week. Now let's see for 19% service level and Z is 2.05. Then the safety stock is 201 units and target stock level is 1,401 units, and the cost of safety stock is $4,020 a week. Supermarkets traditionally use periodic review, and every night the tills pass messages to suppliers to replenish products that were sold during the day. But the system becomes more responsive and reduces stock levels if it sends messages more frequently, for example 2 or 3 times a day. Suppliers consolidate these orders and send deliveries as often as necessary. But why stop at 2 or 3 messages a day when the tools can send messages every time they make a sale? So this is the approach of continuous replenishment. Even the simplest and most automated inventory control system needs some effort to make it run smoothly. For some items, especially cheap ones, this effort is not worthwhile. So very few organizations include routine stationery or consumables in their automated systems. At the other end of the scale are very expensive items that need special care above the routine calculations. For instance, aircraft engines are very expensive, and airlines have to control their stocks of spare engines very carefully. ABC analysis puts items into categories that show the amount of effort worth spending on inventory control. This is a standard Pareto analysis or rule of 80-20, which suggests that 20% of inventory items need 80% of the attention, while the remaining 80% of items need only 20% of the attention. ABC analysis defined A items as expensive and needing special care, B items as ordinary ones needing standard care, and C items as cheap and needing little care. Typically, an organization might use an automated system to deal with all B items. The system might make some suggestions for A items, but decisions are made by managers after reviewing all the circumstances. C items might be excluded from the automatic system and controlled by ad hoc methods. The categories are defined in terms of the value of annual demand, so an ABC analysis starts by calculating the annual use by value of each item. Inevitably, a few expensive items account for a lot of use, while many cheap ones account for little. So listing the items in order of decreasing annual use by value leaves A items at the top of the list, B items in the middle, and C items at the bottom. So now in the table you can see the categories A, B, C, and they percentage and their use by value. Also, this figure here shows typical results of plotting the cumulative percentage of annual use against the cumulative percentage of items. Although they are useful for focusing attention on important items, ABC analysis can be misleading as the annual use by value of an item is often a poor measure of its importance. For instance, essential safety equipment must be available even if it is never used. An assembly line can only keep going if all materials are available, even the cheapest. A medicine may be both cheap and rarely used, but patients hope that it is still available when they need. Location